What's up? It's still me, I guess. Same old opening. This is still the great teacher Alcantara here with another set of videos, and this time around we're going to talk about systems of linear equations in two variables. And it's important to take note that we have to talk about a lot of things. In this case, featuring because she's running around. So this is Evie. So for the first thing that we're going to talk about is about the graphical method, and let's just jump right into it. For this one in particular, we're going to start with the graphical method. But before we go there, it's important that we understand what systems of linear equations in two variables are. So that will be for our learning targets. First is describe what a system of linear equation is using examples and mathematical expressions. Afterwards, we will try to solve systems with the help of graphing. And that will be it. So first, as an introduction, a system of linear equations, it's a system wherein it refers to two or more equations involving two unknowns, for which values are sought that are common solutions of the equations involved. When we say two or more equations, in this case, since we are still in grade 8, we're just going to focus on two given equations. The two unknowns that we're talking about are the two variables x and y. Now, since it's a system, our goal is to identify if there is an existing common solutions, or there's nothing common at all. That's why, as you can see in this screen, you have three possible kinds of solutions. When you have the first one, wherein you have one solution, it's because when you graph those two linear equations, you only have one exact intersection, one point. There are times that we have no solution if the graphs do not intersect. And also at the same time, you can have infinite amount of solutions if your graphs coincide. So to visualize this, we can showcase the concept of the graphical method where you can see the following. If it has exactly one solution, that means your two lines or your two equations, when graphed, are intersecting. If it has no solution, when the equations are graphed, you will have a parallel lines. Two lines that are parallel. And then if you have infinitely many solutions, that's what we call as coinciding lines, as they would like to call it. So in this case, these kinds of solutions actually helps us in identifying the three kinds of systems of linear equations in two variables. We have the first one being a system that is consistent and dependent. This means that the system of linear equations having infinitely many solutions. The slopes of the lines defined by the equations are equal, their y-intercepts are also equal, and their graphs coincide. So an example of this is the given system where we have x minus y equal to 5 and 2x minus 2y equal to 10. We call this consistent and dependent because the slope of the lines are equal, their y-intercepts are also equal, and their graphs coincide. So if you're trying to figure out how were they able to identify if the slope is equal, what you can do is to put both equations in slope-intercept form. So I label this as my first equation, and this is my second one, so that you will not be confused with the solution. So for the first one, let's say that we have x minus y equal to 5. I'll subtract x to both sides so that I could isolate the y variable. I'll get negative y is equal to negative x plus 5. So to follow the slope-intercept form, which is y is equal to mx plus b, divide the entire thing by negative 1 so that our y variable is completely isolated. So you'll get y is equal to x minus 5. So that is your first equation. So your slope here is 1 and your y-intercept here is negative 5. So if you do the second one, you have the example 2x minus 2y equal to 10. Subtract 2x to both sides. You will get negative 2y is equal to negative 2x plus 10. And in this case, divide the entire thing by negative 2 to completely isolate the y variable. Doing so, you will have y is equal to x minus 5. And as you can notice, the slope here is 1 and the y-intercept here is also negative 5. And this is what we call as consistent dependent because the slopes of the lines are equal, and the y-intercepts are also equal. That's why when you graph it, they both coincide. They are overlapping with one another. At the same time, if you pay attention, you can say already without solving or transforming said equations if it is given as if it is the same in the first place. One of the things here that I would like you to understand, to save time, if the question is for you to graph it, you have to do this. But if the question is about identifying if the given equation is consistent dependent, consistent independent, or inconsistent, you may simply manipulate the equations. What can you do there? Sometimes what you can do, if you're not being asked to do graphical method or the other methods, and just by looking at the equations, you can already identify it. If you can simplify said equations. For example, the second equation, 2x minus 2y equal to 10, all of the terms here from 2x to negative 2y to 10 have a common factor, a GCF, which is 2. If you do that, if you divide the entire thing by 2, you will have it as x minus y equal to 5. So as you can notice, what I'm trying to say here is that, again, you can already notice the two equations are the same. And what I would like you to understand, coinciding lines are created or are shown or are graphed based on two equations that are basically the same. They are equal. That's what I'm trying to help you understand here. If you don't want to do the division property, you may do the multiplication property of equality. You may multiply x minus y equal to 5 by 2, the entire thing, and you will get 2x minus 2y equal to 10. And again, this is a way for you to understand if you're not being asked to do any method, and just by looking at the equations, you may manipulate it in such a way that you'll be able to identify if they're the same thing, they're not the same, or whatever it may be. So this might help you out. But if you're being asked to graph, put it in slope-intercept form, identify the slope, the y-intercept, and proceed to graphing. Anyway, let's proceed to the second kind of system. If the system earlier is the same thing, when you simplify it, the second one is not. This is what we call as a system of consistent and independent equations. We say that a system is consistent and independent if there is exactly one solution. Earlier, it's infinitely many because they are overlapping with one another. This one, it is intersecting. So the case here is this. The slope should not be equal, but their y-intercepts could be equal or not equal. So basically, the restriction is about the slope. Okay? We don't care about the y-intercept that much. As long as the slopes are not equal, we can say that the graph is intersecting. So for example, you have 2x plus y equal to 5, 3x minus y equal to 9. Again, you may put them all in slope-intercept form. This is my first equation. This is my second one. Doing so, my first equation, 2x plus y equal to 5. Subtract 2x to both sides, or you may transpose 2x. Either way, you'll receive the same thing. Y is equal to negative 2x plus 5. While the second equation, 3x minus y equal to 9. Subtract 3x to both sides. You will get negative y is equal to negative 3x plus 9. Divide the entire thing by negative 1. And you will get y is equal to 3x minus 9. And you can already see here that the slopes are different. The slope in the first one is negative 2. The slope for the second one is positive 3. The y-intercept here is 5. The y-intercept for the second one is negative 9. So you can already notice that they are both different. And when we say that they are intersecting, the point of intersection is what we call as the solution. It's a fraction, by the way, that's why it's in there. It's not in an exact point in the graph. But either way, again, what we're trying to show here for the second kind of system is that we have intersecting lines. And then lastly, the third kind of system that we're going to discuss is all about inconsistent equations. So we can say that a set of equations is inconsistent if there is no solution. This happens if the slopes are equal, but the y-intercepts are different. So for example, you have here the given 2x plus y is equal to negative 6, and then 2x plus y is equal to 10. As you can already notice, the terms here are the same except for the constants. And we already know that if we put it in slope-intercept form, the constants are our y-intercepts. And that's what we're talking about here of the y-intercepts not being equal. And the slope is basically the numerical coefficient of the x variable. As you can notice, they have two here, both the same. The y's are also the same. But if you want it to be proven using the slope-intercept form, you can have the first equation 2x plus y equal to negative 6. Subtract 2x to both sides. You're going to get y is equal to negative 2x minus 6. The second one, you can have 2x plus y is equal to 10. Subtract 2x to both sides, you're gonna get y is equal to negative 2x plus 10. Again, the slopes are the same, being negative 2, but the y-intercepts are different. The first one has negative 6, the second one has 10. So that's what I'm trying for you to understand here. Basically, again, the slopes are the same, but the y-intercepts are different. So to summarize our kinds of systems, we can put it on a table like this. So for system of linear equations in two variables, we can say that a system is consistent and dependent if the slopes are equal, the y-intercepts are equal, meaning the graph will coincide and the number of solutions is infinite. While if we have consistent and independent, this means that the slopes are not equal, the y-intercept could be equal or unequal, and the graph will intersect, resulting to one solution. While for inconsistent, we have the slope as equal, but the y-intercepts as not equal, resulting to a parallel graph, giving us no solution. So that's how it works. For us to fully understand this, it is now important that we go for the first way of solving systems of linear equations, and that would be the graphical method. So the first one, when talking about graphical method, what we will do is that the solution of a system of linear equations can be done algebraically or graphically. The one that will do algebraically will be elimination and substitution in the near future. While for graphing, we have to find the solution by graphing both equations in the same Cartesian coordinate plane, then find the point of intersection of the graphs if it exists. Why is that the terminology there? Because again, during the first part of our discussion, it was mentioned that we could have coinciding, we could have intersecting, and we could have parallel lines. Okay, so let's start with our first example. We have 3x minus y is equal to 3, and we also have 2x plus y equal to 2. You have the guidance there on the left side of your screen so that you know how to follow through. At the same time, you can pause this video for every time that we do the example so you can try it on your own. So what I'm going to do here is I'm going to label them so that I will not be confused with what equation we're trying to solve. I'll just go with the same thing as earlier. So I'll put them first with our first step by putting them in slope-intercept form. So my first equation is 3x minus y equal to 3. I will subtract 3x to both sides so that I could isolate the y variable. Doing so, I'll have negative y equal to negative 3x plus 3. It's important to remember that if there is no numerical coefficient emphasized for a variable, there is a 1 in there. Since this is negative y, that means there is a negative 1 as the numerical coefficient. Divide the entire thing by negative 1 because again, we want it to be in slope-intercept form, being y is equal to mx plus b. So your y here is none other than equal to 3x minus 3. Because of that, we can identify that our slope is 3 and our y-intercept is negative 3. While for the second one, we can have 2x plus y equal to 2. Put this in slope-intercept form. Subtract 2x to both sides. Oops, why did I write y? Subtract 2x to both sides. You're going to get y is equal to negative 2x plus 2. And here you don't have to divide anything at all because it's already in slope-intercept form. So we could identify the following as m being negative 2, and B being positive 2. So as you can notice, how will we be able to graph this? In the usual method, which is the traditional one, you will draw this on the Cartesian coordinate plane. You have to identify and remember that when we say m is equal to 3, this is the same as having m equal to 3 over 1. Meaning your rise is 3, your run is positive 1. B being negative 3, that means that you can find this in the point 0, negative 3, as said in our guide. Because again, the y-intercept is received by having x equal to 0. Similarly, if your slope here is negative 2, this means that you have negative 2 over 1. So your rise is negative 2, your run is positive 1. And your y-intercept again can be found at 0, 2. So that's how it works. Okay, so once you are able to do that, you may now start by graphing it in the Cartesian coordinate plane. I'll be cheating here a little. I'll use GeoGebra. So if doing so, you can have your first line being like this and the second line being like this. And as you can notice, these two lines intersect at a certain point, and that point being 1, 0. So that is their solution. As you can see, again, they have intersected at a certain point. Intersection is at 1, 0. And as you can notice, our lines are intersecting, meaning this implies that our system is consistent and independent. Why is it consistent and independent? Because there is one solution. How will you differentiate one solution from infinitely many? If there's one solution again, it's intersecting lines. Okay? So there's only one point of intersection, and that is 1, 0. That is our solution. That implies that our system is consistent and independent. So that's how it works. So let's try some more examples. Let's have 2x plus 3y equal to 6, 4x plus 6y equal to 12. It's like earlier, let's make use of this as the first one, this as the second one. Let's have the first one being 2x plus 3y equal to 6. Subtract 2x to both sides. You'll get 3y equal to negative 2x plus 6. Divide the entire thing by 3 so that we could isolate the y variable. You'll get y is equal to negative 2/3 x plus 2, meaning our slope is negative 2/3 and our y-intercept as 2. Next, let's do our second equation. We'll have 4x plus 6y equal to 12. Subtract 4x to both sides. To isolate the y variable, you will get 6y is equal to negative 4x plus 12. Divide the entire thing by 6 to isolate the y variable completely. You will get y is equal to negative 2/3 x plus 2. I think you can see it already with our slope intercept form versions that they are the same thing. So we're not yet done with graphing, but I hope that you guys have the idea on how it will look like. So the slope is negative 2 over 3 also, and the y-intercept is at 2. So your rise here is negative 2, your run here is positive 3. Why did I write run? This can be found at 0, 2. Rise, run, 0, 2 also. So if you look at it in the Cartesian coordinate system, after graphing using our slope and our y-intercept, you will notice that it will look like this. So this is the first equation, followed by the second one. It's gonna overlap, meaning it's coinciding, because at the end of the day, they are the same equations. So they're gonna coincide. So they are coinciding. That's our note, coinciding. Infinite solutions. meaning we will have a consistent and dependent system. So that's how it works. We have a consistent and dependent system because, again, it's coinciding, infinite solutions. Let's try some more. Let's have this one right here. We have 3x minus 2y equal to 6, 3x minus 2y equal to 12. First equation, second equation, let's go. So we subtract 3x to both sides. Let's get it. We'll get negative 2y is equal to negative 3x plus 6. Divide the entire thing by whatever is next to your y variable, that being negative 2. And then that will result to y equal to 3 over 2x minus 3. So we have the second one as 3x minus 2y equal to 12. Subtract 3x to both sides. You will get negative 2y equal to negative 3x plus 12. Divide the entire thing by negative 2. Divide the entire thing by negative 2. You will get y is equal to 3 over 2x minus 6. Now you can see again that there's something that we can notice with the pattern here. The slope here is 3 over 2. The y-intercept here is negative 3. The slope here is 3 over 2. The y-intercept here is negative 6. Meaning the rise is 3 over 2. The rise is 3. The run is 2. The point is at 0, negative 3. Similarly, rise is 3, run is 2, but the point will be seen at 0, negative 6 first. Okay? And if you look at the graph of said equations, it will look like this. Here's our first equation, followed by the second one. As you can notice, these two lines did not meet at all. Yes, their slopes are the same, but their y-intercepts are different, thus resulting into two lines being parallel, having no solution. So that's our answer for the third one. No solution because they are parallel, resulting to a system that is inconsistent. So those are our notes for this example. It's inconsistent, there's no solution, and the lines are parallel. We still have some more examples for practice. So again, you may, if you got it already, it's fine. But if you don't, if you need some more practice, you can pause the video for the items and try it on your own. So for example, now we have 2x plus y equal to negative 8. Then x minus y equal to negative 1. Let's have the first one right here. 2x plus y equal to negative 8. Subtract 2x to both sides. To isolate the y variable, which is one step only, you get negative 2x minus 8. While for the second one, I'll move it a little here. X minus y equal to negative 1. Subtract x to both sides to isolate the y variable. You'll get negative y equal to negative x minus 1. Divide the entire thing by negative 1. Because again, you want the y variable to be isolated completely, positive. So you'll get y is equal to positive x plus 1. So your slope here is as follows. You have the first one having negative 2, and the y-intercept is negative 8. Here, the slope here is 1, the y-intercept is 1. And thus, it's negative 2. This means that you have negative 2 over 1. This is your rise. This is your run. Negative 8 can be found at 0, negative 8. Here you have 1. That means it's 1 over 1. Rise is 1. Run is 1. And this will be found at 0, 1. So that's how it works. So if we graph these two linear equations, it will look like this. This is the first equation, followed by the second one. And they intersect at a point negative 3, negative 2. So that is their point of intersection, thus resulting to a system that is consistent and independent. So this is a consistent and independent system because we have intersecting lines. Just take note of them. Intersecting lines, consistent and independent. One solution. So let's have some, I think, last two examples before we lose our minds. Here we go. So this one right here, we have 2x minus y equal to 2. We subtract 2x to both sides to isolate the y variable, resulting to negative y equal to negative 2x plus 2. We want the y variable to be isolated. Divide the entire thing by negative 1. Thus resulting to an equation y equal to 2x minus 2. Second one, let's go for x minus 2y equal to 4. Subtract 4x to both sides. To isolate the y variable, you'll get negative 2y equal to negative 4x plus 4. Doing so, you have to divide the entire thing by negative 2 to isolate the y variable completely. This will result to y equal to 2x minus 2. As you can notice, both equations are the same. You know what that means. This will have a slope being 2, y-intercept being negative 2, slope being 2, y-intercept being negative 2. I know you're getting the pattern now, but again, it's important that we know what it means. This means that you have 2 over 1 as the slope. This is the rise. This is the run. This will be found at 0, negative 2. Slope is 2. So 2 over 1. Rise is 2. Run is 1. Y-intercept could be found at 0, negative 2. And if you look at the graph of these two things, it will look like this. Coinciding. Coinciding siya. Because again, they're the same thing. So they will coincide. That's how it works. Same equations. Once you simplify, it means they are coinciding. Infinitely many solutions. This is consistent. Look at my handwriting. Consistent, but they are dependent of each other. So you may use those kinds of terminologies like if the word consistent comes to your mind, what can you think of it? If it's consistent, there is an answer. There is a solution if it's consistent. Now, how do you differentiate dependent and independent? It's dependent with one another if they are together, if they are coinciding. Independent when they just pass by one another. So you could think of it like that. Okay? So you may use your own stories so that it will be easier for you to understand. And I guess this is the last example. I guess. I'm hoping. Let's go. Our first equation is y is equal to negative 2x plus 2. Second is y is equal to negative 2x minus 2. Yes. Oh, good example. It's already in slope-intercept form. So all we have to do here is identify the slope and the y-intercept. So in this example, our slope for the first one is negative 2. The y-intercept is positive 2. Here, the slope is negative 2, but the y-intercept is at negative 2. This implies that, again, this is negative 2 over 1. Rise is negative 2. Run is 1. Here, this could be found at 0, 2. For the second one, again, this is negative 2 over 1. Rise is negative 2. Run is 1. But the y-intercept will be found at 0, negative 2. So that will be our starting point for the graphing. Doing so, if you look at the graph, it will look like this. So the first line will look like this one. And the second line will look like this one. As you can notice again, they have the same slope, but they have the different y-intercept. So when you graph it manually, you can already notice that it will result to a parallel lines, two parallel lines. So it's parallel lines because there is no solution. making it inconsistent. So that is it. So why are they inconsistent? Because they never met each other. There's no solution. So that's the thing. Yun yun. Kaya stop stop dreaming if your guys are not meeting at all. It's inconsistent. Or if somebody's inconsistent, stop. Just stop. Just kidding. Anyway, so to summarize this, with our discussion in the near future, we're going to talk about other kinds of systems in different kinds of methods. So we have discussed the graphical method, the coinciding, intersecting, and parallel, and what kind of system is in relation to that. So for our next lessons, we're going to identify what makes a system consistent independent, and inconsistent once we do elimination and substitution method. So that is for next video's discussion. So in the meantime, that's it for graphical method. And that ends the video about solving for systems of linear equations in two variables. Always remember to take note of the examples, practice them on your own so that you'll get used to it and master the concepts. And always remember what's up, and that is respect. And in case you don't see me, good morning, good afternoon, good evening, and good night. Bye bye bye.